This is a video on sampling and data. This is the first video of a 13-part series for elementary statistics, and I hope you enjoy these videos, and I also hope that you learn a lot from them. As we go through these, if you have any questions, please contact me or contact your instructor, get help. Whatever you need to learn statistics is my goal, and I hope that you find these helpful. I hope you end up enjoying statistics a little bit and learning a bit. So what we're talking about in this chapter is first, I'll give an introductory example that talks about sampling and data and populations and all the issues with statistics. Then I'll get into population versus sample. So the goal is to find what the population is all about. The bad news is you never can. So the compromise is we take a sample. Then we'll look at types of data. We have lots of vocabulary to say that if the survey question is this, then the data is going to look like this. If it's something else, it'll look like something else. And then we'll look at frequency tables. So that's organizing data. And then we'll finally talk about issues in data collection, troubles that happen, how to avoid mistakes, how to be ethical, all kinds of different things. So let me start out with an introductory example. So here's our question. Does including a statement about plagiarism in the syllabus lower the plagiarism rate among U.S. college students? Your funds and time are limited. That's a tough question. So what would be great is to go to every college in the country and find out from every student if they've ever plagiarized and look to see if they have had a syllabus that had a plagiarism policy, and then we can look at it. That would be looking at the whole population. And how long would that take, trying to find every student? Forget it. I'm never going to be able to find every student in the country. And there's all kinds of other issues. Well, if you ask a student, did you plagiarize? Yeah, right. My students are going to say, oh, yeah, I plagiarize all the time. So how do you create a question that is going to give an honest answer? And how do you find out what everybody does when you can't ask everybody? And that's what statistics is all about. It's having these questions about the population and then coming up with ways of answering those questions without having to ask everybody. And what we're going to be doing is we're going to be getting a sample of the population. And we're not going to be certain that this sample is representative of the population perfectly, and the answer for the sample is the same as the answer for the population. But it's going to be better than us just guessing. So taking a sample and using statistics is going to be a very good way of making an intelligent guess. So a statement about the population that is most likely correct. Even though it may not be right, it is most likely correct. And statistics is all about that, trying to say, I am very close to certain, maybe 99.99% certain that what I have is also true of the population. We're going to spend not just today, but the entire course on coming up with ways of making sure that very, very close to certainty happens. So let's go on and talk about some of the ways of doing this. So as I mentioned, we often want to collect data. So that collection of data might be asking a bunch of students, do you plagiarize? Okay, or maybe asking the professors, did the student plagiarize? There's different ways of collecting the data. Data may not even be about a person. It may be collecting data from the field and measuring the number of ants that are in a grass field. Who knows what it might be? It may not be people. It could just be scientific experiments based on biology or something. But in any case, we will have collections of observations that we're going to write down or put in a computer and do statistics with. So what does it mean to say this is the course in statistics? So here's what statistics is. Now notice this is the course of statistics, Later on, we're actually going to define what a statistic is. So statistics is the science of planning studies and experiments, obtaining data, then organizing, summarizing, presenting, analyzing, interpreting, and drawing conclusions based on the data. So today, we're going to be mostly talking about planning the studies and the experiments and how we might go about obtaining the data. The organizing, summarizing, presenting, analyzing, etc., that we're going to spend pretty much the rest of the course talking about. How do you interpret and draw conclusions from the data that you've collected? But today, the question is, how do you collect data? So the first thing, as I mentioned, we have to think about what the population is. In our example with plagiarism, the population is the complete collection of all individuals. In this case, it's every single college student in the entire United States. Populations will often be immense. It will be in the millions of people. It'll be in the billions of ants that might be around the world. So the population is usually something you can't get exact statements about. But what you can do is we can collect a sample. Okay. Unfortunately, if we tried to ask everybody in the population, we'd usually run out of time. So if you do ask, though, we call that a census. So a census is the collection of all the data from every member of the population. It's actually written in the Constitution of the United States of America that every 10 years we must conduct a census, and we have to ask every person in the United States. And we do our best on that. It costs billions of dollars and takes years to do. For most studies, you don't have billions of dollars, and you don't have years to conduct that study. Usually you might do it in a day, and sometimes you don't have any money at all to make it happen. A census is usually impossible, or at least impractical to do, and we don't do a census. So instead, we take a sample. And a sample is a sub-collection selected from the population. So that may mean the 100 students we asked about plagiarism. It could be 500 grass areas that we counted the ants in. So that's a sample. Every sample has a sample size, and that's the number of individuals that you surveyed or you looked at. If you do want to collect a sample, it's always a good idea to take a random sample. But it turns out taking a random sample is very, very difficult. So first, what is a random sample? A random sample means that any individual is just as likely to be chosen as any other individual. So here's a problem. Let's suppose you wanted to take a random sample of students at your college. If you went around your college and you randomly picked people, you would almost certainly be doing it wrong. It is very difficult for any individual to pick random people just by kind of looking around the room and saying, no, you, and I'll pick you and you and you. They've actually done psychological studies and found out that people are much more likely to select people that are like themselves when they're attempting to create a random sample. So instead of doing that, what is much better is if we can use a computer. If we can get every individual put into a computer database and then use a random function on the computer. And trust me, the random functions work very well. I'm also a computer programmer, and I know how they work, and I'm not going to explain it. The math is very deep. But just trust me, they work really well. And a computer can pick a random sample of individuals. Person is not very good at picking a random sample. Even if I asked you to pick a random number from 1 to 10, good old random sample, right? So I'll give you a second. Pick a random number from 1 to 10. Okay, you got your number? Okay, very, very few people will pick the numbers 1 and 10, whereas 20% should. Okay, I'm pretty close to certain you didn't pick 1 or 10. In fact, you probably picked 2, 3, 4, 6, 7, 8, or 9. That's what almost everyone picks. So psychologically, we have troubles with random samples. On the other hand, computers can do it very well. And if you ask a computer to pick a random number between 1 and 10, it will. The next type of random is actually kind of complex. So let me state it, and then I'll give you an example. So that's called a simple random sample. And what that means is that every possible group of n individuals is just as likely to be chosen as any other group of n individuals. So let me give you an example of something that is random but not simple random. Let's suppose you wanted to pick 10 cards out of a 52 card deck. And hopefully you know that card decks have 52 cards, 26 are black, and 26 are red. So what you do is you're going to pick 5 of the cards to be red and 5 to be black. And you'll use a computer, actually, to pick the 5 red cards and to pick the 5 black cards to get your 10 cards. Hopefully you're convinced that that will be a random sample. Every single card is just as likely as any other card to be picked. And that's because we made sure that half are red and half are black. This is actually called a stratified sample, and we will discuss stratified sampling later on in this lecture. But for now, we see that it's random. This is not a simple random sample, and here's the reason. Let's look at the group of 10 individual cards that are ace of spades, 2 of spades, all the way up to 10 of spades. That's a group of 10 individual cards. All are black. Well, since we're picking 5 black cards and 5 red cards, there is a 0 probability of picking those 10 cards that were all black, because we're going to pick 5 reds and 5 blacks. On the other hand, if we looked at the 10 cards consisting of ace of spades through 5 of spades and ace of hearts through 5 of hearts, that could happen because there's 5 blacks and 5 reds, and it may not be very likely, but it's not a 0 probability of picking those 10 cards. So we see that there are 2 groups of 10 individuals. One group has a 0 likelihood, and the other has a non-zero likelihood. Those are different likelihoods. So picking in that way, even though it's random, it's not simple random. So anytime you have stratified sampling, we'll talk about that later, but that basically means that you're asserting that you can have a certain number of each group, then we don't have simple random sampling. So let's move on and talk about this type of sampling. So one type of sampling is called systematic sampling. This is used especially when we're talking about products, for example. So for example, if GM wanted to test their airbags in all of the cars that they made by crashing them into a wall. Well, that'd be expensive. GM is not going to test every car to make sure that the airbags deploy after crashing it into a wall, because it'll destroy every car they have. So instead, what might they do? Well, instead, they might pick maybe every 1,000th car that is produced, crash that 1,000th car into the wall and see if the airbag works for that 1,000th car produced. And let's suppose that they made 100,000 cars of that type. Then they'll have a sample of size 100, and that sample will be a systematic sample because it's every kth car, in this case, every 100th car. So again, this is done very well when you can actually put things in order. It also works if we want to, say, survey students. Then we could maybe survey every 10th student who registers for classes this term. And that would be a systematic sampling. Another kind of sampling is called convenience sampling. This is a sampling that is never good for any kind of reliable study. And that means we just select whatever's easiest. So maybe you post on Facebook, "Hey friends, please answer my question." And then you have 50 friends answer your question, and you say, "Aha, Well, I took the average of the friends, and this is what I know about. Well, that is called convenience sampling. It's terrible because it has all kinds of issues. It's only people that answered your question. It's only your friends, and your friends they may be wonderful people, but they're all a certain type of people. They are your friends. So convenience sampling is a bad idea. We need to do some kind of scientific sampling. That could be random using a computer. It could be systematic. It could be stratified. Stratified means subdivide the population into groups and establish quotas to ensure that each group has the same proportionate representation in the sample as it has in the population. So here's an example. Let's suppose that I want to do a study of students at my college to find out if they buy food daily at our bookstore. And I want to make sure that I don't have a bias that is a gender bias. So I want to make sure that we have a gender representation of the college. I could ask, let's say I want to ask 200 students. I could ask 100 men and 100 women, but that actually would be biasing towards men. Because it turns out, because I've done my research, and I've found out that 55% of the students at the college are women, and 45% are men. I need to make sure that I have a proportionate amount of men and women. So if I take 200, that's my sample size, and multiply it by 55%, I get 110. And if I take 200 and multiply by 45%, I get 90. So I will ask 110 women and 90 men if they buy food daily at the bookstore. And then I've ensured that I don't have a gender bias. I could have other biases. And often stratified sampling will include many different strata. Strata could be gender. The strata could be the ethnicity, could be age, income, many, many different types of characteristics can be classified as strata. But no matter what you do, you always have to first do your research. Could be a little check on the internet to find out what the proportions are. It could be going to the library to ask the librarian what the proportions are. But one way or another, you have to do a quick little research, and then stratified sampling is pretty easy. The final kind of sampling I want to talk about is cluster sampling. So let's suppose you want to find out the widths of the pine trees in the Tahoe area. You can't measure them all. We have millions and millions of pine trees. If you've been to Tahoe, you know we have trees and trees and more trees. The other problem is the Tahoe area is huge. So if we, say, stratify it by 1 tree per acre, then that would be awful because we'd have to travel. I mean, it's beautiful here. It's nice to hike around all the acres. But it could take years to go through all the acres in the Tahoe area. So instead, we could do what's called cluster sampling. And that means we divide the population into many sectors, then randomly select a few sectors and choose all members from those chosen sectors. So we might pick North Tahoe, South Tahoe, East Tahoe, and West Tahoe. Those are the 4 sectors of Tahoe. And then we might pick 1 acre. Okay, we'll look at all the acres in the different places, and we can pick 1 acre from each of the 4 different areas. So there are maybe thousands of acres, maybe even millions of acres in the Tahoe area. We're going to pick 4 of those acres. And then we're going to measure every single tree for each of those 4 acres. And that's cluster sampling. And that's a lot easier than having to do all the traveling you might have to do throughout Tahoe. Imagine if it was all of America, how much traveling you have to do. Another way of doing cluster sampling is at colleges. So there are natural clusters at colleges. In fact, those are called classes. You go to the classes at the college, and you don't want to go to all the classes because that bothers too many students. So you might select maybe a math class, an English class, maybe a history class, an art class, maybe a fire science class. And then you go to those classes, just them, and you ask every student in those classes. That's called cluster sampling. Let me talk about some issues that happen in designing a study. So the first is voluntary response, and this comes up a lot in, say, telephone interviews. So have you ever been asked, have you ever been called on the phone by somebody saying, I have a survey, and will you please answer a maybe 10-minute survey? And what'd you do? You hung up. Okay? Honestly, I'll be honest, I've hung up before too. Maybe it's not the nice thing to do, but sometimes you do it. I always hang up politely, but I hang up still. And once in a while I do answer. But there are certain types of people that will answer the question and others that don't answer the question. So if you are only looking at the people that answered your question, which is all you can look at, then you only have that type of person. And that could bias your study. So that's called a voluntary response bias. Ways around that, I was once called, instead of saying, will you please answer my survey with, a very nice begging, it was, I will pay you $100 to answer this survey. And guess what I did? Absolutely. $100? Definitely it's worth my time. And I answered the survey. And then they probably didn't have a lot of voluntary response bias because people are going to answer the survey if they're given $100. The problem with that is it's very expensive. Another way around voluntary response is using authoritarian ways of doing it. This is done in colleges, actually. If a professor asks you to fill out the survey in class, you're going to do it because you do what the professor says, because that's how our culture works. Another big issue, this is probably the biggest issue that I have when I work with, say, a grad student or a researcher that comes to me and asks for help with their statistics, and that is sample size. Just recently, I had someone ask me to help with their study that they did. I looked, and they'd only asked 8 different people. Actually, they did a research project where they did an experiment with 8 different items. 8 turns out to be way too small a sample size to run statistics with. So we will later in this course talk about how big a sample size you need, but I'll tell you now, the bigger the better when it comes to having reliability, but of course bigger takes time and money. So sample size is a big issue, and you have to make sure you have an appropriate sample size to run statistics. Another is the wording of the survey question. So for example, if I asked you, people in the community, do you support funding colleges more than they're funded now? And do you support helping these students so that they can really end up with a great education? Versus, do you support raising taxes and taking more money out of your income so that college students who otherwise could just get help by their parents can have kind of an easier time with college? Well, basically they're the same question, but you could see the wording is really different. So depending on how you word the question, the person will answer differently. So you want to make sure you word it as an unbiased way as possible. Sometimes you give the pros and cons first, and then you ask the question. Question and response order is another issue that happens. It turns out that for psychological reasons, being first is more likely to be chosen. So one way of handling response order issues is you actually use a computer to randomize the responses, and you make many, many surveys, same question, but the responses are in different order. And that way people are less likely to just choose the first one each time. They may choose the first one, but that first one is going to be different for everybody. Any of these issues will result in bias. So a good study, a well-designed study, will avoid bias as much as possible. I want to spend a very small amount of time talking about probability. We actually have 3 full chapters in this class to just address probability. So first, probability is a measure of the chance of an outcome occurring. If you can count, then we say how many ways are there of an outcome occurring, and how many ways are there of that event that you're looking at happening. You divide, you get your probability. Probability is always between 0 and 1. You can't have a negative chance of something happening, and you can't have more than 100% of something happening. And then finally, if S represents a collection of all possible outcomes, then the probability of S is equal to 1. So if I say I'm going to pick a card from the deck, what is the probability of either getting a spade, a diamond, a club, or a heart? Well, that's a 100% chance because that's all the cards. If I pick a card, it's going to be one of those, so the probability is 1. Okay, next I want to talk about parameters versus statistics. This is a big theme of this class in that the goal is to get an idea about the population. You can't survey everybody in the population because the population is too big, so you take a sample. So a parameter is a numerical measurement describing a population. So that could be the mean weight of all Americans. There's no way in the world we are going to find that out because by the time we weighed everybody, it would probably take 100 years to do that. And guess what? Everyone just died, and now you have a new 100 years of American people to weigh. So it's just not going to happen. So instead, what we do is we take a sample. And we take a statistic from the sample. And a statistic is the numerical measurement of the sample. So that would be, we take 200 Americans, randomly surveyed, maybe using stratified random sampling, if we can, and we weigh them and take their average. Their average, the average of those 200 people from the sample, is called a statistic. So other parameters in statistics would be, say, the population range, and a statistic would be the sample range. There are many. There's maximum, there's minimum, there's something called standard deviation, which we'll talk about later on. There are many different types of statistics and parameters that we can look at. Once we have decided on the survey question, we want to say, well, what kind of answer are we going to have? So first we can break it up into two types, quantitative and categorical. A quantitative survey question, so quantitative data, means they are numbers. The answers are numbers representing counts or measurements. So that might be, how much do you weigh? How tall are you? How many seeds did that plant produce? On the other hand, categorical, often called qualitative data, means names or labels. They are not quantitative. So that might be, what is your favorite color? Or what state were you born in? Those are categorical questions. Another would be something like, have you ever been to Africa? That's a yes-no question. We're going to spend a whole lot of time in this class talking about that yes-no question. Let's break up quantitative data further. I'm going to break it up into two types, discrete and continuous. Discrete data means that the outcomes that occur are a result of counting. So the survey question might be, how many siblings do you have? Well, I can count the number of siblings I have. I happen to have 3 siblings. Okay, or 3.5 if you count half siblings or step siblings. Okay, so that means that you can count them. I have 1, 2, 3, 3.5. Okay, others might be things like, how many pairs of shoes do you have? I can count my pairs of shoes. I know some people that have trouble counting their pairs of shoes. They have so many, but you can count them. Whereas continuous data are outcomes that occur as a result of measuring. So that might be, how much do you weigh? Okay, you look at the scale, and that's 165.325 pounds. And that would be continuous data. That means you measured instead of counting the how many. Let's break up into even more. We could talk about levels of measurement. So the first level of measurement we've already talked about, and that's called nominal. I haven't given you the word, but in any subject there's lots of words for the same thing. Qualitative can also be called nominal. That would be like, where were you born? I was born in California. You might have been born in Texas. Notice it's a word answer. Next is ordinal, and that means it has ranking, but you can't measure differences. So one example of that is called the Likert scale. That would be such as, how much do you agree with this statement? We should tax the rich so that we can decrease the disparity between the rich and the poor. Strongly agree, agree. Disagree, strongly disagree. Notice it's qualitative, but it's more than the other kind of qualitative because we can actually say that strongly agree in a way is higher than agree. And that's ordinal. Another would be, what medal did you get in the Olympics? Gold, silver, bronze, or none? That also has ranking. The next level is called the interval level. And that means we can measure differences, but we can't say something like it's twice as large. So the two main examples are time of day and temperature. So we could say that I woke up an hour later than you woke up. So I subtracted our wake-up times, and I got 1 hour. But it doesn't make sense to say, I woke up twice as late as you woke up. That's just is silly. Similarly with temperature. Okay? I took my temperature, and my temperature is 2 degrees above normal. I have a fever. But it doesn't mean that I have a 2% higher temperature than normal. That you don't talk about it that way. So that's called interval. The next type is ratio. And that means we could do all of this, and we can talk about being twice as large or 5% greater. So that'd be weight or size. So, for example, it does make sense that that guy's age is twice as old as his girlfriend. Okay, that makes sense. That would be ratio. If you have a choice in the type of data, choose ratio. In fact, choose as much math as you can do. I know you may not love math, but you want to be able to do math if you can when you're working statistics. The next thing I want to talk about is with and without replacement. So first, let's talk about with replacement. So I like cards because I understand those pretty well. Let's suppose I pick 2 cards out of the deck. I'm going to pick the first card, look at it, not replace it, not put it back in the deck. I'm going to keep it in my hand. And then I'm going to pick another card. And I want to find out the probability that I get 2 aces. This is called without replacement because I'm not replacing the card. The probability of getting 2 aces without replacement, you can trust me, is about equal to 0.0045. Later in this course, we'll actually learn how to compute that probability. But for now, just believe me. The other way of picking 2 cards is with replacement. So that means I pick a card, I look at it, I put it back in the decks, I mix the deck, and then I pick another card. That's different. And in fact, if I find out the probability that both of those are aces, I get 0.0059. Because I haven't pulled out a first ace to get that second ace, I put it back in the deck, and I can still get that same ace. So with and without replacement are different when the sample size is relatively large compared to the population size. On the other hand, if we're, say, picking a sample of size 100 out of all Americans, and there's 320 million Americans or something like that, then the sample size is very, very small compared to the population size. And in that case, with and without replacement are basically the same. You have to go a lot of decimals out for any differences to occur, and you don't have to worry about it. That's all I want you to really know is the difference between the two, and that for large populations compared to the sample, it does make a difference. Okay, now let's talk about error. And there's going to be 2 types of error I want to address. The first type is called sampling error. And that is either errors in design or just bad luck. So for example, one design error, the sample size was just small. So if I asked, even if it was like perfectly random, if I asked 5 Americans out of all of America, how much they weigh, well, I could just get bad luck and end up with a bunch of fat people and end up with a huge amount. And if I think that that's representative of all Americans and that is the American average, then I'm out of luck. I guessed wrong. So another issue that could happen is it may not be representative of the population. That's that bias. So maybe I posted on Facebook and I did a convenience sampling. That is a sampling error. It's an error in the way I sampled. So there's lots of different sampling errors, but it really has to do with the process of sampling. It's not a mistake I made. It's either just the design was not perfect. Another type of error is called non-sampling error. And that means it's a mistake in the data collection. So for example, if I asked 1,000 people how old they are, and somebody answered, I'm 54 years old, but accidentally I typed in the computer 45. We've all made that mistake before where you switch the numbers. That's a non-sampling error. Not the result of a small sample or some kind of bias issue. It's just a mistake. I typed it in wrong. Another mistake that could happen is I may weigh a lot of people, and maybe the scale is wrong. It weighs people wrong, okay? The machine is wrong. That means it's a non-sampling error. And the next thing I want to talk about are frequency distributions. They're things you've probably seen before, so I'm going to briefly discuss it. So first, a frequency distribution table in this case is a table that shows the number of values in each category. So I ask people in the class, how old are you? And I had 19 people between 15 and 24 years old. I had 8 people between 25 and 34 years old. And I had 5 people between 35 and 44 years old. And I draw a table, and that's a frequency distribution table. Not much to say about it. One of the things you have to decide on are how wide you want your intervals to be. So if you decide, say, you want to have 4 different intervals, then how wide should you make each interval? Okay, and it's best to have each of the intervals of equal width. That way you're not misrepresenting the data. So if you can, sometimes you can't, but if you can, make them equal width. The class width is the difference between 2 consecutive lower class boundaries. Let me show you what I mean. So here's a table with hats versus frequencies. Okay, and you can see we had 0 to 4, we had 6. We had 5 to 9. There were 14 people that had between 5 and 9 hats, etc. So we don't want to go 9 minus 5. That's not the width of the interval. The width of the interval is actually 5 minus 0. So it's the low of the interval we're looking at minus the low of the one just before. The way you compute a class width to decide how wide you should make it, if you know how many classes you want, is this formula right here. We say the width is equal to the maximum minus the minimum divided by the total number of classes that you want. And this up arrow means round to the next whole number. So if we did this arithmetic and we got 3.8, we'd round to 4. If we got 3.2, we'd round to 4. If we got 3, we'd still round to 4. So always go to the next whole number up. And that gives you the width. So let's suppose that I did a survey and I asked a whole lot of people how many units they were taking. And the person taking the most units took 28 units, way too busy. And the person taking the least was just taking 1 unit. And I wanted to look at 3 different class intervals. So I take 28, that was the maximum, minus the minimum is 1. So 28 minus 1 is 27. And I want to divide that into 3 classes. 27 divided by 3 is 9. So I don't make the width 9, I make it 10. And that's how you calculate the width. So let me talk about relative and cumulative frequencies. So a relative frequency distribution means instead of frequency, we look at the contribution of each interval. So what we do is we take the frequency and we divide by the sample size. What that does is it takes large frequencies and turns them into percents, okay, or proportions. And that way we don't have to deal with very large numbers. So instead of saying 150,223 people scored higher than 1,800 on the SAT, we can instead just say 14% scored higher, or 0.14 of the population scored higher than 1,800 on the SAT. And that's a relative frequency. Cumulative frequencies mean that instead of frequencies, what we do is we look at the number at or below that particular class or that particular value. So for example, you might not be interested in the exact number. You might be interested in how many at or below that number if you want to say how many will fit in that box. So we might have 6 box sizes, and you want to say how many will fit in a middle-sized box. Small things will fit in the middle-sized box, middle things will fit in the middle-sized box, and big things won't. So if the box fits things at most 1 meter tall, then anything 1 meter or less will be counted for that frequency. You might have another box that is 1/3 of a meter tall. Then anything less than or equal to 1/3 of a meter will count for that cumulative frequency. So the next thing I want to talk about, and this is something that a lot of people have trouble with and misrepresent statistics, and that is cause and effect. So a lot of times you want to say, did this cause something else? That's a very difficult thing to explore. So an example might be, this is an example that happened to me. I saw an article in the newspaper that says, if you have the runs, run to the VA hospital and be part of this experiment and take this new medication. And I was having a bad day. I don't need to get graphic about it. So I went to the VA hospital. They gave me this medicine. Then a week later, I told them how I felt. Okay? So the variable was, did I receive the medicine or did I not receive the medicine? Okay? That is the explanatory variable. The effect is I was feeling fine after a week or I was not feeling fine after a week. That's called the response variable. The treatment is the value of the variable. So in this case, yes, I received the medicine, or no, I didn't receive the medicine. Okay, sometimes you could do for medicine, it could be how much medicine you received. For my particular one, it was yes or no. Often what you do is you break the sample into 2 groups. The first group we call the control group. The control group does not receive the treatment, and the treatment group is the other group, and it does receive the treatment. So, for example, when I did my little medicine example, I unfortunately was the control group. What that meant was they gave me a pill, and that pill didn't contain anything that had anything to do with medicine. So I got what was called the placebo. So I was in that control group, and they compared the control group with the treatment group. And they did it by using what's called a placebo, which means I actually didn't know, and we'll talk about it in a bit, I didn't know that I was getting a piece of medicine that did nothing. It was just a sugar pill or something. And they do that to control for lurking variables. One lurking variable is if you know you got the treatment versus if you know you were in the control group, you may get better because you feel like you should be getting better. Okay, that's called a lurking variable. The knowledge that you got the treatment instead of the treatment itself is an example of a lurking variable. It's something that might cause both. Another lurking variable, so for example, they did a study and they looked at children who were abused, okay, children that were screamed at and hit a lot, and then they looked later in life to see whether they abused their children. You might say, well, abusing children makes children end up abusing their children, but maybe it's genetic. Maybe that people who have that abusive gene have children who are abusive, and guess what? The grandchildren might be abused also. So that would be a lurking variable. So it's not that abusing the child caused the next child to be abused. It might be an abusive gene. So as I mentioned, I received what was called a placebo. And here's how that particular experiment worked. What they did is they took all the people in the study. Let's say there were 500 people in the study. 250 of them were randomly selected to be the control group, and 250 of them were randomly selected to be in the treatment group. Then what happens is that each person receives a placebo in the control group, and in the treatment group, each person receives the medication. The people in the control group don't know they got the placebo, and that's called blinding, because I was blind to the fact that I got the placebo. In addition, they could do a double-blind experiment. And that does not mean they poked my eye out, both of them. What that means is that the doctor giving me the medication also didn't know who got the medication and who got the placebo. There's a third party, the researcher, who actually makes the pills that are placebo pills look exactly the same as the pills that are medical pills. And the doctor just writes down some serial number, and the doctor has no idea what the numbers mean to identify control versus treatment. So the doctor doesn't know either. What that means is that if you don't do double blind, then the doctor may feel so bad that they're giving someone a placebo that the doctor's facial expression might kind of make the patient feel bad and feel like they're not going to be getting better because the doctor was treating them differently. So if the doctor doesn't know and the patient doesn't know, we call it a double-blind experiment. Okay, finally, I want to finish off with a little bit of statement about ethics. Statistics often gets a bad rap, and it's not because the math is poor or incorrect or wrong or anything like that. It actually has to do with two things. One is people just don't trust statistics. They don't understand it. But there's another thing that could happen too, and it does happen, unfortunately. Honestly, I have never been unethical, but ethics is a big issue. So one of the things that can happen is that the experimenter can falsify the data. That should never happen. You should never do that. So that's the old, well, I don't like the way my data looks, so I'm just going to erase a couple of them and no one will notice, and that way I could publish and become famous. And yes, that does happen. Okay? And hopefully it won't happen to you. Hopefully you will be ethical. The other piece of the ethics has to do with poor ethics on hurting people. So for example, when I was in college, very long time ago, I had a girlfriend actually. She was required to be part of an experiment. That was part of her grade actually. And she was very unlucky to be part of the pain experiment. And what they did is they put her through some horrible pain, and they wanted to see how she would react. Okay, nowadays things have changed. Now every experiment has to go through an ethics committee. And something like that at a university would never make it. And that experiment just wouldn't be run because it's just cruel. So cruelty isn't allowed anymore. Okay, another issue which I talked about is cheating. So again, don't cheat. Don't cheat, don't cheat. I've known people to cheat, and it's just bad. Companies sometimes will cheat so that they can get their product approved, or they can advertise that their product works when it really doesn't. The other is just plain ignorance. So do your research. I have looked over a lot of people's statistics that might be psychology majors, might be business majors, and it's not that they're unethical, it's not that they cheat. They just don't get it. Their sample size is too small, and they don't understand that when you have a small sample size, you can't perform certain statistics that they want to perform. And it's because they don't know, not because they're bad people. So the way to deal with ignorance is a couple. One is do well in this class, learn statistics so that you're not an ignorant person. The other is if you have something that's really important, people's lives might rely on it, and all you've done is taken one elementary statistics class, it's probably not enough. Once you're my student, you are always my student. You can always come to me 10 years from now, ask me some questions, I'll help you out. So ask an expert and get help and make sure that you are doing it correctly. Or even better, take this class, elementary statistics, and then take a whole lot more classes and become a statistics professor or a statistician and become the expert and not be ignorant at all. So that's another way of dealing with ignorance. So that's all I have to say today. I hope you learned a bit and these concepts came pretty easily to you. If not, or if there's any confusion you have, go back, look at the video, or ask me questions. If you have another professor, ask that other professor questions about these concepts, or ask your friends, ask a tutor. But whatever it is, don't just pretend that you don't know it and move on. Get help so that you really get this stuff. When you are learning statistics, the number one reason that people fail is they just figure that, well, I don't have the time to do it today. Maybe tomorrow, and then tomorrow happens and they don't do it. They don't check up on it. And then pretty soon they're so far behind that they just lose it and they drop the class or fail the class. So make sure that you stick with it. Spend the time, spend the hours that are needed, and there are many hours needed to learn statistics at this level so that you really learn how to analyze data, conduct surveys, and as this course moves on, interpret that data and come up with really good conclusions. So I hope you all have a wonderful day, wonderful week, wonderful hour whenever you're watching this. Just have a wonderful time, and I'll see you in the next lecture, which is all about the statistics, the mean, the median, the mode, the standard deviation, all the ways of analyzing and drawing charts like histograms and stem and leaf plots and box plots and pie charts. So how to do descriptive statistics. I'll see you next time. Goodbye.